Thank you very much for a kind introduction. And foremost, I want to thank the organizing committee for inviting me to speak at this year's symposium. As you have seen from the title, I will be speaking about the use of NDE technologies in condition assessment of bridges. Considering that what I have seen from the program, that we are going to have a very diverse group of interests, from structures to materials to payments and geotechnical issues. I will not be too technical, but I hope that some of the things will be some thought-promoting things. So when we speak about bridges, yes, and something what attracted me maybe to civil engineering was wonderful concrete bridges. And while we recognize that they can be beautiful, we also recognize as engineers and researchers that those structures deteriorate. And the question is, so what we can do about those? So my approach to condition assessment and monitoring of concrete structures, I always like to say is that we can draw a complete analogy with how we manage our own health. We can say that certain principles like prevention, diagnostics, early intervention, and overall health monitoring, that it is going to lead to our better lives, longer lives, and that we will spend less money for medication, for doctors, and so on. And the same we can say for our infrastructure, for our bridges. That the only difference is that we are not speaking about better lives, we are speaking about better performance, we are speaking about longer lasting bridges, and finally we are, from the point of bridge owners, they are spending less money for the management of their pool of bridges. So we cannot speak about all of those, but I will speak today about one element, and that is diagnostics, and more specifically, I will concentrate on the use of non-destructive evaluation technologies for their condition assessment and monitoring. So while everything what I will be speaking about, we have used in evaluation of all bridge components, but my talk will concentrate on concrete bridge decks. And the reasons are the following. First, bridge decks, because of their direct exposure to both live and environmental loads, they are deteriorating faster than other bridge components. Something what we have learned from the discussions with a number of bridge owners, number of state DOTs, is that they are spending more than 50% of their available monies on rehabilitation, maintenance, or repair or replacement of bridge decks. So this is of the highest interest for them, how to manage effectively concrete bridge decks. So what we will try to discuss today is a little bit, can we improve bridge management by receiving more accurate information, and that information is going to come from non-destructive evaluation. One of the elements, what is always related to the cost, is how fast you can collect data and how fast you can process data. So what is critical is automation of those NDE data collections. And finally, in every bridge management system, is to be able to do good planning, you need to have good predictive models. So I will be also speaking a little bit about deterioration and predictive modeling. So these are main parts. In the first part, I will provide, so to say, an overview of NDE technologies which we are commonly using in condition assessment of bridges. We will move and speak briefly about automation of NDE data collection. And the last part will be related to knowledge creation in deterioration and predicting modeling through both field NDE surveys and also data collection in our accelerated structural testing facility. So a little bit about NDE technologies which we commonly use. So what is of common interest when we are evaluating condition assessment? These are typical deterioration or defect formation types we find in concrete bridge decks. So corrosion very often initiates deterioration, delamination. Delamination, if you're not familiar, those are very fine cracks, which typically span between rebars. So those are pretty much horizontal cracks. We are interested in concrete degradation. And what typically we see from visual inspection, we are interested in these surface breaking cracks or vertical cracks, what you see at the bottom. So if we would like to be able or to be in a position that we can evaluate all of those potential sources of deterioration, we cannot do it by a single technology. We have to rely on a number of technologies, and we can also relate those technologies to typical deterioration progression. So what you see on this slide is a typical, we can say, bridge deck condition deterioration curve. And we can say that deterioration typically starts with corrosion, not always, progresses into delamination, and finally leads to spalling. So if we start with this process with corrosion, we can say the process starts with, we can say, forming of corrosive environment. So intrusion of moisture, chlorides, salts, other chemicals. That is what is going to create corrosive environment, and that corrosive environment can be well characterized by electrical resistivity. Low resistivity means high conductivity, and that is what we can expect if we have moisture, chlorides, salts, and so on. So once we have developed corrosive environment, at one point we will initiate corrosion, something what we would describe as corrosion activity, and which can be detected and measured using half-cell potential. So as we move to, as deterioration progresses, we have cracking, delamination. Probably the best suited methods to detect the delamination are acoustic methods. Probably most widely used method is impact echo, but we're also using ultrasonic echo. You can also see some other methods, infrared thermography. It is also a good method, but it is pretty much conditioned by the time of the day when you can do it, and you can typically detect only shallow delamination and also, you may say, relatively wide delamination. So to illustrate what are typical results from surveys using NDE Technologies, I will go to this bridge, which we surveyed as a part of long-term bridge performance program for Federal Highway Administration. This was the only one opportunity which maybe anybody got to survey a bridge by NDE Technologies 4 times. And we surveyed this bridge within 6 years, 4 times. So how it typically looks like on a bridge. So you can see a bridge deck with a marked grid. This is a washable paint, and it marks fairly fast. We deploy all technology at once, and typically at a rate of about 1,000 square feet per hour, we collect the data. So a bridge like this one, approximately 2 6-hour shifts. So just to very briefly describe technologies and devices we are using to assess. So on the left side, you are seeing electrical resistivity. This probe is called Venner probe. So it has 4 electrodes, and in a very rapid manner, you may say within a fraction of a second, you are measuring the resistivity of concrete. On the right side, you see a rolling half-cell probe, which I mentioned is used to assess corrosion activity. So let's see some typical results. So for example, for this bridge, what you see in those different colors, cold colors indicate sound condition, while warm and hot colors indicate problems. So for example, in this case, those red zones represent zones of very low resistivity, and those are the zones where you can expect that you will have high corrosion rates. If you go from top, which is the map from 2009, to the bottom, which is the map from 2015, you can clearly see there was progression of deterioration. this environment became more and more corrosive. And so we had a larger area, and we also had more severe, we can say, corrosive environment. Very similarly, for half-cell potential, describing corrosion activity, if you go from the top to the bottom, again, warm colors indicate zones of what are described as very low, very negative potentials. And you can see that there was a very clear progression of that corrosion activity. Moving to the next technology, Impact Echo. We are using different devices. Probably now we are most commonly using the one on the right side, which we call Impact Echo Cane, and this is what we built ourselves. On the left side is another device, Stepper, which is, you may say, semi-automated system with multiple Impact Echo probes. So what we are doing with Impact Echo is, it is like a mini sonar device. You are looking for reflectors somewhere within that concrete bridge deck. If reflector is the bottom of the deck, you know that it is sound. If there is a shallower reflector, you know it is delamination. And again, if you would go from top to the bottom, you could see that there are more and more of those red areas. Finally, two methods which can describe methods for concrete quality assessment. On the left, you can see ground penetrating radar, electromagnetic method. This is a method where we can say is from the measurement of attenuation of electromagnetic waves reflected from top rebar mesh. We are assessing potential deterioration in concrete bridge decks. The method is such that you can describe it more as a qualitative method, because you are never certain, for example, is there maybe delamination there? Is it just corrosive environment or something else? But high attenuation is typically an indication of some deterioration processes. On the right side is a quantitative method. It is called ultrasonic surface waves. So see this device at the bottom, which is called portable seismic property analyzer, where we are, by using surface waves, by measuring the velocity of surface waves in concrete, we are actually measuring concrete modulus. And in that case, we can say really we are having a quantitative measure which can be compared between different points or between different surveys. Just as an example of those maps, so for the same bridge, Haymarket Bridge, you can see 4 maps from ground penetrating radar testing. Again, those dark red zones describe zones of very high electromagnetic wave attenuation, which are probably zones of deterioration. So now when we have presented the data in terms of those condition maps, very often for management, especially on the network level, we would like to describe the condition of every bridge deck by a single index. And something what we are using is called condition index, which represents nothing else but a weighted average of percentages of deck area in different conditions. So what you see here on the top, these are, for example, according to ASTM, according to criteria from ASTM, zones of this concrete bridge deck with 90% probability of active corrosion, something what is uncertain, so transition zone, and percentage of area with 90% probability of no active corrosion. So once we have those percentages, we can use very simple formula like this one at the bottom, weighted average, to calculate this condition index, which is in a range from 0 to 100, where 100 represents perfect condition, while 0 represents the worst possible condition. And you can see, for example, how this condition index changed with respect to corrosion activity during those 6 years. So this can be done for every technology, and here you can see summarized condition indices for this particular bridge during those 6 years. There is a very clear and significant decrease in the condition of this concrete bridge deck. And while maybe those points are not sitting on a perfectly smooth curve, they clearly indicate a trend of deterioration. And just to give you, to compare it, what is the practice? And the practice for most bridge owners is to use just visual inspection and evaluate, for example, what is described here, condition rating of the bridge. So for example, for the same bridge, when we pulled condition rating from National Bridge Inventory, it showed that this bridge deck did not change condition rating 6, not just between 2009 and 15, but since 1992. For almost 25 years, there was no change in condition. And you probably can ask yourself it is probably very challenging to have good management if you have to make some predictions based on such data. So what is an additional benefit? So I could probably list about 10 or so different benefits, but another benefit is, for example, if you compare these zones from different technologies, you might say top 2 maps represent electrical resistivity, half cell potential. So these are measures of corrosion. And when you look at the map below, the lamination map, it matches pretty well where we have significant corrosion, which is telling us that probably the biggest driver of deterioration in this particular bridge was corrosion. This is not always the case. And in the second part of my talk, when I will speak about accelerated testing facility, corrosion was not the main driver. It was fatigue from repeated high intensity loading. And this is what we have seen on real bridges. So one of the reasons why NDE technologies are not widely used is because, yes, it is labor-intensive activity. And whenever you have labor-intensive activity, it also costs. So NDE technologies are being used, but still not widely. So one question is how we should do, if we would like to conduct NDE surveys on a network level, how we can do it more economically. And what we have, for example, shown is that while we conduct on project level surveys on 2x2 foot grid, that if you compare these maps from the top, 2x2 foot map, grids 2x6, 4x8, well, they look a little bit different, but not that significantly. And for example, when we would evaluate condition index from this very fine and fairly coarse grid, we are not going to spend too much time here, but the difference is on the order of 10–15%. So you may say that you are, for example, if you would like to give a single grade, a condition index, that condition index is not going to be significantly different if you work on a much coarser grade. Okay, what is also good about these condition maps is on the network level, if you would like to provide very intuitive presentation, we have done it in different ways, but for example, for the network level, probably the most convenient one way would be to place those maps in Google Maps. So you simply, for every bridge, it has its own coordinates, you can recall those condition maps. And here you can see on the left side, there are all the maps for this bridge, and you may go from one year to another, and in a very intuitive way, recognize what was the progression of deterioration for any particular structure. Certainly, where we are probably investing the most time for concrete bridge decks, at this time is probably in automation of NDE data collection. I will be speaking a little bit about the robotic system which we have developed, but there are a number of automated systems which were developed at other institutions. So maybe one difference is that this is fully autonomous system. and that it deploys 4 NDE Technologies, other automated systems which are much more rapid than this one in terms of data collection. They typically deploy a single or maybe 2 technologies. And one of the reasons why this is not as fast a system is because we have to have contact measurements. So this is a robotic system, Rabbit, which deploys 4 NDE Technologies. What you see on the front end, acoustic arrays. Those have multiple impact echo and ultrasonic surface wave devices. There are 4 electrical resistivity probes on the front end. And you see on the rear end, there are ground penetrating radars arrays. So these are not just single antennas. Each of those white boxes has 16 antennas. Another important additional element are those digital cameras on the top, which, so to say, they're not replacing or substituting visual inspection, but they are making a permanent record of the surface of the bridge deck. So here you can see how Rabbit is operating. It is fully autonomous system. There is nobody operating with a joystick. The way how it is being done, we take 3 GPS coordinates. There is also GPS base station. And after that, an algorithm will develop the path and this robot will freely move. At the end of a single strip, it is going to rotate in place. And then it is going to translate to the next surveying strip. The robot was, or we can say its NDE arrays were designed intentionally to be 6 feet wide so that they can cover half of a typical lane width. So 2 passes are sufficient to cover the entire lane. One of the important contributions of this full automation is safety. So under such conditions, this is New Jersey Turnpike, it would not be just unsafe to collect data manually, it would be extremely uncomfortable so by having this fully autonomous system with its safety measures, it is much safer and much faster to collect the data. So the condition maps obtained from Rabbit are very similar to what you get from manual technologies. So I'm just going to show one additional element. So what we can do from those cameras. So there are numerous photos which are being stitched together into large images of the surface of the bridge deck, which can be examined at any time. And here you can see, for example, on the top, if we would like to examine section A, that section A is shown below. And then further, if we would like to examine this joint, point C, you can have a close-up of that, and you have a permanent, so to say, visual inspection record. So let's go now to the last part of my presentation, which is related to deterioration and predictive modeling based on NDE surveys and accelerated structural testing. So if we go back to the data from Haymarket Bridge, we have already presented those, but in that graph, all the points were covering the period when we conducted surveys. But if we look into the entire life of the bridge, that life started in 1979. So that is the point on the right. So we don't have any data between 1979 and 2009, 30 years. And the question is, so what did happen between the starting point and the end point? The starting point, the birth, and the first survey. So the first question we can ask is this really correct that we assign as initial condition that it has condition index 100? And what we have learned, for example, from our own sample in our accelerated testing facilities, no, you should never assign condition index. You should better take measurements to be sure that this condition index is 100. So this speaks about the importance of baseline measurement. And the second element, what we would like to learn is the shape of the curves as it was assumed here. So to be able to get this very first part of the curve, we are looking into experiments in our accelerated testing facility called BEAST, so Bridge Evaluation and Accelerated Structural Testing Facility. So you see here the facility while it was still under construction. You will see how it looks fully enclosed. But here you can see some of the elements of that structure, but the most important elements are that this facility can accommodate bridge structures which are 50 feet long, up to 24 feet wide, and about 5 feet deep. With respect to the loading which you can apply, there is a dual axle carriage, which can carry load of 60,000 pounds. And this load can move at the speed of close to 20 miles per hour, or make approximately 15,000 passes per day. In addition, we can apply environmental load, and there are two primary elements. Yes, there is an environmental chamber where you can continuously control temperature, but we primarily use that environmental chamber to vary temperature to simulate freezing and thawing during winters. And in addition, there is salt brine spraying. So this is now fully, so to say, enclosed facility. So what you see, those covers, they are enclosing that environmental chamber. So the whole bridge structure is inside the chamber. To illustrate how this is working is, we will start first with animation, which was when we envisioned how this facility was going to work. And then you are going to see a little bit how this carriage is moving on this bridge deck. So the bridge deck can be prefabricated and put in place, or our first specimen was actually built in place. And once it is in place, there is this dual axle carriage, which is moving, I said, approximately 15,000 times a day. So you can control environmental conditions. So we have spraying, but not from the ceiling. It's done from the side. You can control temperature. If you would look very closely on the left upper corner, you will see the temperature is going to freezing right now. And now it is heating up, going to much higher temperature. So the objective is really to drive temperature sufficiently low and sufficiently high to have freezing and thawing. And so this was the idea. Is yes, we will have a number of cycles. We typically go with about 250,000 cycles before we go with evaluation of the condition using NDE Technologies. Something what was initially envisioned that we would be using Rabbit to do data collection. No, it is not done by Rabbit, it is done manually. You may say the surface is still too small for Rabbit. And now you're going to see how this carriage is moving. So it is just the start of the test. And so speeds approximately close to 20 miles per hour. And this is not just in one location. The carriage can be moved laterally. So we are testing at the different locations on this lab. Here you can see the preparation of the very first specimen. So there are 4 steel girders. And you can see the finished concrete deck with the grid, which is marked for NDE data collection. So here we are going to, with, you may say, super fine resolution, we are collecting data on 1 by 1 foot grid. There are a number of technologies. So 5 technologies I have mentioned, but we are also deploying some other technologies. We don't have time to speak about all of the results, but I am going to show some of the results. So first, a little bit about baseline measurements and why those are very important. For example, to build this concrete bridge deck, there were 4 truckloads of concrete. So we usually assume that concrete quality is the same, but the results both using ultrasonic surface waves and from the cores taken to the lab and evaluated there. Yes, there are differences, and they NDE Technologies and lab results match. For example, zone number 2, the highest modulus measured in the lab was also the highest modulus measured using NDE Technologies. What was critical for this specimen was concrete cover. And while this was a research project, the company, it seems they did not place properly their screening machine. And what happened is that concrete cover, which was supposed to be 2 inches, was 2 inches near the joints. And in the middle section, or let's say approximately middle 20 feet, was about 1 inch, an inch to maybe 1.25 inches. And this showed up in results, that it was the main driver of deterioration. So from all of the results, I will just show you results from one technology, modulus evaluation using ultrasonic surface waves. So how the results changed as we went from one survey to another survey. So here we see some variability, but all of these cold colors, greens and blues, indicate everything is fine. So 240 days, 360 days. Here we are starting to see something happening. Lower modulus in this middle section of the bridge with thin concrete cover. And as we go further to 590, we are starting to see very low modulus. And that very low modulus is really not truly low modulus of concrete. What is happening? It is a result of formation of delamination. When delamination is forming, it is going to lead to apparent low concrete modulus measured by ultrasonic surface waves. And this will be progressing, ultimately giving a plot like this, where we have plenty of delamination and we also have some spalling. So if we would try to quantify how modulus changed during this experiment, so you can see in truly approximately 840 days of how long the facility was operating, that this concrete modulus, first there was a decrease in average modulus, but also there was an increase in standard deviation of that modulus, which typically means like we are having higher variability of the modulus. Both are indicators of deterioration. What you can also see on the top graph, which shows the loading which we have applied during this experiment, is that there are a number of these flat portions which represent interruptions. Some interruptions were during the pandemic, initiation of the pandemic. It was spring and summer of 2020. Some of them were because there was a need for some maintenance in the facility, but it was hard to get maintenance, replacing ropes and so on. So there was interruption, and certainly there were shorter interruptions to collect the data. So if we would eliminate all of those interruptions and present data like we had uninterrupted operation of BEAST facility, everything what we have achieved actually was achieved during 151 days. So and something what I would describe based on what we have seen on actual testing of bridges is probably, or not probably, it is definitely more equivalent to 10 years of actual bridge life. So cumulative live loading, so there were more than 2 million passes. There were about 120 applications of brine, and there were about 100 cycles of freezing and thawing. And finally, to illustrate how critical that concrete cover was for deterioration processes in this bridge deck. The top orange curve represents the curve for the sections close to the joints of the bridge, so where we had 2-inch cover, while the bottom line, blue line, represents the modulus in the middle section, so where we had thin concrete cover. And you can clearly see that there was significant degradation with respect to delamination. So these are impact echo data. Moving to the concrete quality data from ultrasonic surface waves, 2 inner curves representing average modulus and standard deviation for the middle section, 1-inch concrete cover. You will see a significant drop in modulus and significant increase in standard deviation, while for the zones close to the joints, you can see that average modulus did not change much, and standard deviation did not increase much. So there was far less, there were only a few signs of deterioration in those sections. And finally, just to illustrate with respect to corrosion, corrosion activity from half-cell potential. If you look at the orange line near the joints, 2-inch cover, there was basically no significant drop in condition index with respect to corrosion activity. On the other hand, when you look at the blue curve, where we saw thin concrete cover, we had significant development of corrosion activity after those 151 uninterrupted live loading days. Some of these zigzagging of the curve, that is because we have eliminated those interruptions. And what would happen is during those interruptions, concrete would dry, corrosion activity would become less pronounced. And once we would again start with the testing, start spreading brine, then we would increase. But in general, we can see that there was significant increase or degradation with respect to corrosion activity. Ultimately, what we obtained from all of the technology, what we learned from, for example, half-cell potential and electrical resistivities, that corrosion was definitely not a driver. We calculated what was approximately mass loss due to corrosion, and that was very minor. So it was not the driver. So what was the driver was fatigue due to repeated high-intensity live loading. And this was especially pronounced in those zones of thin concrete cover. And just to illustrate how visually things change. So this is from left to right. This is just the change of the surface during a 2-month period. So to end my talk, I would like to go with a few conclusions. I hope that you have seen 2 elements. First, that taking baseline measurements is critical. Knowing whether the material is uniform as it was designed, whether you have a sufficient concrete cover, whether rebars are placed correctly. And that is what we can do with NDE surveys. What you have also seen that from periodical NDE surveys that we can monitor very accurately condition change, and we can quantify it. It is very hard to quantify it based on visual inspection. If you were talking to people who are providing services using NDE technologies, very often you might hear that they are advocating for certain technologies. Is how we should view is that we should not see different technologies as competing, but we should always think about their complementary use, because every technology has its strength and it has its limitations. And therefore, if you would like to get a comprehensive assessment, really it can be done only using multiple NDE technologies. What you have also seen is, and I mentioned this, one of the reasons why NDE technologies are not being used on a network level is because of the cost. And you may say a little bit because of traffic interruptions. So this can be in part overcome through automation, but also if you are using manual technologies by collecting data on much coarser grids, the data will not be significantly different. Certainly everybody now would like to concentrate and develop different automated systems for rapid data collection, but also for rapid data analysis and interpretation. And with respect to data collection is, first automation is going to lead to improved speed of data collection. It is going to enable safer data collection and less traffic interruptions. And what you have seen from the robotic systems is if you mount multiple technologies, it really doesn't matter whether you're having one or 4 different technologies. And finally, as a research tool, we have high hopes that we will learn quite a lot from accelerated structural testing, that this testing is going to help us develop fundamental understanding of deterioration processes in concrete bridge decks, and what is of the highest importance for bridge management, that it is going to help us develop more accurate deterioration and predictive models for concrete bridge decks. So with this, I thank you very much, and I would certainly like to acknowledge not all, but the most what I have presented was done with the help through a number of years from Federal Highway Administration from its long-term bridge performance program. So thank you very much.
Any questions? Yeah, thanks. Great presentation. And, a lot of really interesting technologies. So right now, it seems you guys are doing this mostly by doing periodical assessments every once in a while. Are there any NDE technologies that are continuously monitoring health and for local damage, or trying to maybe predict damage before these periodical surveys?
Well, for that, we would really need to, so to say, embed sensors. The only technology which I would describe that can be placed permanently is, for example, infrared. Cameras can be mounted on poles, and you can take images whenever you would like. So that is probably the only technology which we can describe is NDE technologies. What you are talking about, more continuous monitoring, that would probably fall into SHM, structural health monitoring arena, and that is typically related to placement of some sensors.
Then you mentioned that not automatically assign score of 100 to new possibility of construction elements.
Absolutely, absolutely. For example, I have shown results for our research lab, and the error was, so 2-inch cover was not 2-inch. Maybe we are happy now that yes, it provided us maybe an additional experiment we did not expect. But what we have seen is we have surveyed, I don't know how many bridges, actual bridges, and one bridge I would say is major bridge, which we surveyed using ground penetrating radar. The specification was 2.5-inch concrete cover. We were finding zones anywhere from 0.5 inch to more than 4 inches. That is what we were finding, and there is no question that those zones with very thin cover, they were going to deteriorate fast.
I got a question from online audience. Very interesting work. Thanks for Professor Gucunski. What question from the data analytics perspective? Do you think the data collected by NDE Technologies from one infrastructure can be reused? Given that collecting data is possible, collecting data for every single for a long period of time would be very challenging.
That is correct. And I remember many years ago, there was, I was interested in payments, NDE of payments. And I remember some of my colleagues who were in asphalt curve, in asphalt research, they were developing master curves. And this is what I hope is that we will also end up with some kind of master curves. Yes, similar like with asphalts. Yes, every material doesn't follow that master curve, but they are close. And that the more we learn, that we will be able to develop master curves, and that we can say is like by having those curves and maybe having a single or only two measurements, we will be able to say approximately what we can expect, what is going to happen with the performance of that bridge deck or maybe other bridge component. But all of the technologies, what I mentioned is we have used on other bridge components, on piers, on pre-stressed girders. So everything can be used.
So if I can chime in,
First one, you predict the actual raw data.
Yes. And actually those data, LTBP program, those data will be available to general public. So everybody who would like to use. And maybe I would use this opportunity to let you know is, you know, this BEAST facility is opens opportunity for many of you. While we are conducting, for example, this study, which was of interest to Federal Highway Administration, it doesn't mean that in any future studies there is so much space for some of the work you do, whether it is material related, sensor related, and so on. So please feel free if you recognize an opportunity where some of the research of interest to you could be embedded into whatever might be the driving study for Federal Highway Administration. And we will be happy to discuss and, if possible, implement.
One of your conclusions says you observe any enhancement of particular by corrosion?
Okay, I'm not sure. I understood every element of your question, but with respect to corrosion, one of the reasons why we did not observe significant corrosion probably has to do with time. Because when we speak about, yes, we have corrosion activity, but you might say that mass loss is integration of time. And so we would need to find the way. We would either need to have very extremely high corrosion activity, very high corrosion rate to achieve significant corrosion. And that is something what we will still need to learn how to do it. Maybe I did not respond directly to your question. But when we calculate, for example, we ended up that we had approximately loss of about 40 microns on the rebars in the middle section.
Actually, if I may supplement that conversation, I would say corrosion, because depending on the quality of the concrete, the time period to initiate corrosion could be very lengthy. In the field, it's supposed to be 35. So the diffusion takes time for enough for us to get onto the rebars. But once it kicks in, it starts very very problematic and will interact more with the big factor. But in the early age, it's like a dormant phase where probably that's what we're observing.
Yeah, so what we have done is, for example, we were using various correlations done on experiments of correlations related to mass loss based on measurements from electrical resistivity, based on the measurements from half cell potential. But to get to that mass loss, so you are integrating all of those measurements with time, and based on those integrations is yes, the overall mass loss was such which we do not describe as a significant.
We go one further question from the online audience. Could you elaborate on the mass curve? What type of factors, features should be taken into consideration in order to learn the mass curve?
Which elements should be? Well, certainly one of the elements should be what is the predominant driver of deterioration. At least based on the experience we had so far on different bridges, we have primarily noticed that the drivers are either corrosion or it is fatigue. And we are, for example, right now conducting various simulations where we are trying to see what kind of difference in deterioration progression we are going to observe if we have, so to say, fatigue of material due to repeated high intensity loading. And we are also doing some simulations which are related to crack formation as a result of corrosion. And we are going to see is whether we are going to get a little bit different shapes of those master curves. And all of those combined with the data we have collected in the field and the data collected in BEAST facility, we hope that it is going to help us to get as good as possible master curve. Just simply looking, for example, into when I was looking into data for corrosion relationships between whether it is half cell potential data, resistivity data is, I would say, those are still very crude relationships. So I also expect that those master curves, they will have general shape, but they will require continuous improvement.
So
no, we have not. We had, for example, one project with Federal Highway Administration, but that one was not related to post-tensioning. It was related to pre-stress elements.
the reason I asked, everybody tries brown.
Yes. No, but you know, I would say some of the NDE technologies like impact echo, ultrasonics, they can be used, for example, to measure, to evaluate how good grouting is. It can be, but we haven't evaluated, for example, the effects on the corrosion of post-tensioning.
Actually, I want to use that conversation on the master curves. I would say, when your overall quite different now. The other thing is when you're using animation confirmation design, some of the master curves will. So there are a lot of other things that could complicate this task.
And we will need help from experts in those areas. So we would welcome anybody who is interested in joining in some of these studies.
Sorry, I did one question which is related to you know, at the coarser scale, you say, well, it's very efficient, you know, so you can do network level NDE and assist the bridge management. But at the project level, the finer scale, have you, you know, looked into essentially the data fusion or even the machine learning approaches. to
Yes.
Leverage whatever you collect, this kind of information.
And actually, machine learning we are already using, and that is to improve interpretation of the results, and is especially for electrochemical and electrical methods, electrical resistivity and half cell potential. Because, for example, if we speak about half cell potential, where you are measuring, so to say, the potential of that electrical field, it certainly makes a difference whether you are measuring with a probe which is 1 inch above the rebar or 2 inches. So some correction should be done for concrete cover. Also, the correction should be done for moisture content.
Okay.
Correction should be done for temperature. These are all of the elements, and actually we have used electrical resistivity, and that is where we are saying is because we have data from multiple technologies, for example, GPR, which is telling us concrete cover, delamination can affect the result. We have data from ECHO. If you would like to assess moisture content, we are using one technology called Moist Scan, microwave technology, which can provide at least, we can say, qualitative assessment of where you might have very high moisture content. So by combining all of those technologies, feeding the data into this machine learning algorithm, we are actually correcting. I had one slide and I took it out, which exactly showed this, how we can, by using data from multiple technologies, we can improve interpretation of each one technology. Yes.
Yeah, impressive work. Yeah, I just have some question for clarification. So, basically, the mapping of the modulus, one of the mapping, the map of the modulus. So, because the modulus might be varies, so do you have an average value?
Yes, we are measuring, we are describing it as an average modulus. There is definitely variability, but that would again require the process which we call back calculation inversion. And we have pretty much seen that on an average, it doesn't matter that much. But if, let's say, for research level, you would like, yes, it is also possible to give some assessment of variability with depth.
Yeah, from the result, from the X-ray testing is not the photo image. So we have that subject testing, there's a location to have like clearly say that certain distance.
Yeah, there is a
correlation to some depth, like some distance.
Yeah, what you saw, those red zones, those are zones where there is delamination. And what is happening there is when you place a device, you have placed it on delamination. So the energy of the wave cannot propagate deeper. So you're getting some strange reflections, and that typically shows up as a very low modulus. And we know it is not measurement of modulus, it is a presence of delamination. But if you have delamination, it is worse than having lower modulus.
Not sure what are the additional questions. I guess we're approaching the end of time, so let's have a 10-minute break.
Thank you very much.